This webcast continues the discussion of the lab conservation of momentum, and we are at the conclusions of this lab. Okay, so there are some fill in the blanks here, and we'll just read through and try to think about what goes in each blank. So first, it says recall Newton's third law of motion. In every interaction, there is a pair of forces acting on the two interacting objects. The size of the force on the first object equals the size of the force on the second object. The direction of the force on the first object is opposite to the direction of the force on the second object. So in summary, forces always come in pairs, with the two forces having equal magnitudes and opposite directions. In a collision between two objects, both objects experience forces that are equal in magnitude and opposite in direction. Such forces often cause one object to speed up, meaning it gains momentum, and the other object to slow down, or in other words, to lose momentum. According to Newton's third law, the forces on the two objects are equal in magnitude and opposite in direction. However, the accelerations of the objects are not necessarily equal in magnitude. In accordance with Newton's second law of motion, the acceleration of an object depends on both the net force and the mass of the object. So therefore, if the colliding objects have unequal mass, they will have unequal accelerations, right? Their accelerations will not be the same as a result of the contact force that results during the collision. Within an isolated system, momentum is conserved during all collisions, whether elastic or inelastic. And the law of momentum conservation can be stated as follows. For a collision occurring between object 1 and object 2 in an isolated system, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. That is, the momentum lost by object 1 is equal to the momentum gained by object 2. In equation form, we have the momentum of object 1 equaling the negative momentum of object 2. This statement, which we just saw above, tells us that the total momentum of a collection of objects, in other words a system, is conserved. That is, the total amount of momentum is a constant or unchanging value. Okay, let's give a little more description of elastic and inelastic collisions. For all collisions in an isolated system, momentum is conserved. In some collisions in an isolated system, kinetic energy is conserved. A perfectly elastic collision is one in which the collision causes no loss in the kinetic energy of the system. An elastic collision is defined as one in which both conservation of momentum and conservation of kinetic energy are observed. This implies that there is no dissipative force acting during the collision, and that all of the kinetic energy of the objects before the collision is still in the form of kinetic energy after the collision. An Inelastic collision is one in which some of the system's kinetic energy is redistributed to a different energy storage mode, such as sound, heat, changes in height, and/or deformation of the objects during the collision. Most collisions are inelastic because some amount of kinetic energy is converted to potential energy, usually by deforming one object or by raising one of the objects higher, therefore increasing gravitational potential energy. The only commonly seen elastic collisions are those between billiard balls or ball bearings because those balls do not compress or dent. Collisions in ideal gases approach perfectly elastic collisions, as do scattering interactions of subatomic particles, which are deflected by electromagnetic force. There are some large-scale interactions, such as the slingshot-type gravitational interactions between satellites and planets. Those are perfectly elastic. Okay, and then we want to summarize a little bit about explosions. The same principle of momentum conservation can be applied to explosions. An explosion is a special type of collision. It is a perfectly inelastic collision that seemingly happens in reverse, right? Before the collision, all the objects are stuck together, and after the collision, all the objects are moving apart from one another. In an explosion, an internal impulse acts in order to propel the parts of the system into a variety of directions. After the explosion, the individual parts of the system, and that is often a collection of fragments from the original object, have momentum because they are moving. If the vector sum of all individual parts of the system could be added together to determine the total momentum after the collision, then it should be the same as the total momentum before the explosion. Just like in collisions, the total system momentum is conserved. Okay, and that finishes our conclusions.